Today we have a third degree polynomial with what you might call parameterized coefficients. The parameter is p in this case. And we're given that two of the roots are multiplicative inverses. And so we can arbitrarily say that AB, there's three ways we could choose these roots. I'm just going to go AB, stay alphabetical. AB is equal to 1. A and B are multiplicative inverses, and that's a condition. And by the way, I don't think specifying that they're integers is necessary here. In fact, I'm almost certain. And also, no need to specialize that they're rational roots or specify. I don't think you can be the judge in the way the problem is worked out, but probably the rational roots is necessary. Okay, but we're supposed to find the values of p, singular or plural. P stands for product because the product of the roots present right there, and you can see this if you expand out. This is just an expansion using A, B, and C as the roots, and when you expand it out, negative the sum of the roots presents as the exponent of x, as the coefficient of x squared, and then the pairwise products summed up present as the coefficient of x, and finally minus the product of the roots appears as the last part. That's very easy to see when you just expand this out. This is kind of tedious to write this all out, and I didn't show the work, but notice that the minus sign appears here and here. So and it also appears in front of the sum of the roots. And so you see, in a way, when we equate the coefficients, the minus signs just go away since they're present in both representations. Okay. So anyway, when you equate the coefficients, you get these three statements, and convince yourself of that. It's just a direct comparison of the given polynomial with the polynomial where the roots are part of the expansion. Okay. Now, since AB is equal to 1, you can see we get, if 1 is right here, okay, you're going to subtract 1 from 347 to get 346, so we get this simplification. And also we quickly get that P is equal to C, which is super useful. Okay, P is equal to C since AB is equal to 1 and P is equal to ABC, right? So this is very, very useful, and that's tantamount to saying we'll be done if we can find C. All right, so all our efforts here are towards getting C isolated. Now, here, this one's kind of going from here. You may see, okay, this is a given condition, or from the equating the coefficients. Now, notice all of a sudden we jump to here. Well, we know that P is equal to C. Now, what about this piece right here? Well, that maybe is the perhaps hardest one to see, but you can factor out a C, and you have A. Right here, if you factor out a C, you have A plus B quantity, or just the sum A plus B times C, right? It's just factoring out C. Okay, that's a B there, folks. That's a B. A plus B times C. All right? And that's where this 346 over C comes from. See right here, here's this C right here is the C right here, but A plus B, when you divide it, 346 by A plus B is just equal to C. All right, or I didn't say that right, but you can see how the algebra works out right here, how this term A plus B, okay, is equal to 346 over C just by inspecting this term and looking right here. Okay. So that's the part that was, quote, the hardest, but it was really not that difficult. All right. Now, at this point, it's very straightforward. You can multiply through by C. Notice that C can't be a 0 because it's just the way the problem is set up. Or let's see, can it? I guess it's, well, we're assuming that C is not equal to 0 here. So that's a little bit of a leap, I guess. But there's no real clear reason why it would not. It's possible that it could be equal to 0, I suppose. Or no, if it was, the product would be equal to 0, right? So yeah, C can't be equal to 0 because ABC is not equal to 0. All right. So wait, I think but in any event, I multiplied through by C right here, and you get this statement right here. If you multiply through by C, you get a fairly easy quadratic without a linear term. And that's very easy right here. Just multiply everything inside by C. And again, we are assuming that C is not one of the roots. Just assuming it. I don't know if the original prevents that, but we're assuming that C does not equal to 0. So anyway, when you multiply through by c, you get this quadratic. And it's very easy to see how this works out. Now, the hardest part here, we get c squared is equal to 27,225. And a little bit of effort is required to notice that that is a perfect square. You could go through and divide through by fives, and you would get nothing but even exponents if you wanted to. And I'm not going to go through that process with you, but what we get is c is equal to plus or minus. And why is that important? C is equal to p, right? But because of the strong condition that two of the roots have product 1. Okay? So we have plus or minus the square root of 27,225. And with a little bit of inspiration and perspiration, you would get this is equal to 65. And it's something you can do. It's not too bad. Divide by 5, and you'll eventually get to a point where you have a prime factorization, and all of the exponents will be squared. Okay? So the answer here is c is equal to plus or minus 165, but of course that's equal to p. And we did this without finding that. We know that one of the roots is 165. We don't know the other two. I guess you could come back here and figure it out. But anyway, so this is equal to p also. So those are our two integers. And again, they turned out to be integers, but the math, stating that they were integers at the beginning was unnecessary. The math would just take care of that for us. So those are the two values, folks. And again, we don't know A, B, and C. I don't see any immediate ways. Let's see if P, we might be able to figure out A and B. I'm not sure, actually, though. Could we? Yeah, well, we could, because since we know what P is, we could just go back and do the rational zero theorem if we felt like it, right? Since we know P, we could go back and do the rational zero theorem and then do some checking. But I think that would be the only way to do it, right? I don't think I've got enough here. Just because I know that P is equal to plus or minus 165 doesn't mean I can find the values of A and B explicitly. So this, I think, is still one of those problems where, I mean, you can, but it's just a lot of work. You can't do it from the work that I've shown here, okay? So this is kind of a type of problem where you can find a result without finding some of the constituent results, which is kind of interesting. They're common in math competitions. All right, that's all.